的倍数。
2的 n 次，所以它要派定第5，所以原来的 data 它要先做一个这样子，然后得到16384。好，假设这个我的数理问题给你设一个16384，然后它利用这个东西去做，就 data 进去做 FFT。FFT 的时候才有一个数据，所以那这两个数据会影响这个可以解。
这个我还真的不知道，我不知道它是怎么搞的。但是这个 fast food 参数里面有好多那个 trick。
因为
这个是它那个它处理前一个还是它那个 Welch 号 spectrum。
是 FFT，
没有 FFT。那你没有用它的那个，它那里有一个 GC Welch。你看，你到那了。
它那个数据我给是有的时候有个数据就是2分之8，就是傅立叶积分的那个数据。
那个积分的数据是那个积分是在变，因为你要看你的，对，你那个积分呢，那你要看你是做hertz 还是配合R。
对，那还有一个所以的时候
这个 n 是因为它整个做成那个富瑞积分呢，富瑞积分不是抽成 n， 抽成mean 是 RMS。
对，可是我现在因为我是12000点得到16384，那我今天是要用12000，16384，就会影响这个结果。
影响抽手的 energy。
对，就是这个数据。我又给老师讲了。
这是问他们那个专门写富瑞，看他这个。那你假如派了以后要除 n 的话，就
我就先除 n 再取那个 absolute value。
然后把那个
对，现在那个就是
我想他那个 n 恐怕不是用最后的，因为那个富瑞算出来那个 RMS 都是对的，积分出来都是 RMS。那个都没有问题。Okay, let's start. Let me remind you that you have to hand in your homework. Otherwise, I will not be able to give you a grade. Okay? Please give me by today, so that I can read all the papers on the weekends. Okay? All right. Last time we talked about the bridge, and we talked about the deck of the bridge. Today we're going to go down to the piles. This actually are the data that you have a very heavy truck passing by the bridge. You can look at the truck on the bridge. What the data is obtained by a accelerometer put right on the deck over the pile. Okay, so you can see that this truck drives by. This is a lot of vibration, and if you look at this data, it's pretty hard for you to tell which piles actually are healthy or which piles may have problems. But if you look carefully, you can see that here you have some pretty noticeable periodicity. But the periodicity is also available here. So it's hard to say hard to say based on this to see which piles has problem. Now remember, in health monitoring, the magnitude usually doesn't count. It's the frequency variation that we are looking for, because the magnitude sometimes depends upon the sensitivity of the sensor and the gain and all that. So this magnitude, we should not pay too much attention of the result. Of course, the input magnitude is important. Now, the previous one were two very heavy trucks. Now these are some light cars like this one. This particular one is a Benz. It's very quiet and passing by the piles. And there are some other intermediate sized trucks. So I made a Hilbert spectrum of the two piles. This is pile number 1. The primary energy actually is around here and over here. So around here you see that at this point actually is where the truck passing by the pile. Now you see that this energy is around near 2, but slightly below 2. And this is, as I say, pile 1. And this is pile 2. Pile 2, again, the main energy is over here and here. This is the largest energy spot. And if you look at this point, you will see that frequency actually decreased. Okay, for pile 2, the frequency gets lower. All right. Now, once we have this Hilbert spectrum, we do a marginal spectrum. Here we have 4 different different spectrums. First, let's look at this. This is a Fourier spectrum for pile number 1 and Fourier spectrum for pile number 2. Now you see that their peak actually line up, the second harmonics and all the harmonics are lined up. But there are differences in the magnitude. As I said, magnitude cannot be a good discriminator for the structural response. Yeah. Now this pile number 1 is slightly has a lower energy, but the peak location are all the same. However, if we look at the spectrum, the Hilbert spectrum, then we see that the peak frequency actually shifted. And the amount of shift, it looks small. This is around, this is 1. This is around 1.2, this is about 1.6. Okay. 1.2 and 1.6, the ratio is 4 to 3. Yeah. But for frequency, the vibration of a structure member, the frequency is proportional to square root of the stiffness. So if you square this 4 to 3, you have 16 over 9, which reflect the stiffness. And that means the stiffness of this pile is almost half of that. Yeah, because 16 over 9, it's 16 over 8 is an exact half. So this is almost lost half of its stiffness. Now, this of course is only one load, and if we analyze all the different loads and make an average, now these are all different trucks passing by pile number 2, and these are all pile number 1. Now you will see that pile number 2 and pile number 1, it's different. They are different, even in the mean. The higher frequency, however, the frequency is the same, but the lower frequency, it's different. Not only that, we can also calculate the mean of pile number 3 and pile number 4. So the average of pile number 3 is over here. It's identical to pile number 1. But pile number 2 set really aside and very different from pile number 1, 3, and 4. And this is average over many piles. If we can plot it like this, say pile number 3 and pile number 3 and pile number 4, you can see this the difference. Their peak almost line up. I have staggered the magnitude. I have plot this a little bit lower, and the average of all this is actually this spectrum, and this is average. This is mean of 3 and 4. This is pile number 1, and this is pile number 2. So the frequency shift, the frequency change is clear. Now, the last time we say that to judge the structural health, we should not wait until the frequency change, because frequency change is very difficult to achieve. Sometimes you have 20% cross-section loss, the frequency still does not change that much. Okay, so what I suggest is try to look for nonlinear oscillation. But here, clear the frequency already changed. And that, based on the structural vibration theory, we know that half of its stiffness has already lost. So it seems that the HHT can make a difference in bridge safety monitoring, and we should not rely on frequency downshift alone to determine damages, because this is very insensitive. Nonlinear characteristics revealed under heavy load versus light load are critical. I strongly recommend that we look at this as a way to indicate whether the structure is or is not damaged. A comparison between damaged and undamaged span is critical. For bridge, this is easy, but for building, it's not that easy, because the building has a lot of redundancy. You take any building, you have so many different columns, so many different beams, and if one of the beams is damaged, and if you're further away from that beam, you will never see any difference at all. So, by comparison, bridge is a much simple, easier problem to do. Now, then we look at the damping spectral analysis. Now, this is based on the work by my colleague Li Ming Savino at the Naval Surface Warfare Center, belongs to the U.S. Navy. What she did is trying to extract the damping characteristic of a structure. The damping characteristic of the structure actually reflects the characteristic of a structure. But in this particular application, the damping is even more important, because what they are studying was the damping of the submarine. Yeah, if you have a submarine, and if the submarine get hit, and you want the shake to stop right away. If the shock continues, it may damage your equipment, it damage your machinery, and also cause damage to personnel. So, in the past, they were using modal analysis. The modal analysis is time domain versus frequency domain, the single degree of freedom, and the single function, and all that, linear assumption, everything. Yeah. So the damping actually is computed from this mode. Each mode you can write as as A times EI theta t. But this A is a function of time. The oscillation is a function of time. You write this A as CE minus psi t. Yeah. See, this psi is actually what measures the damping. If you take the derivative of this, you find that that is psi t actually is defined as the damping rate. Yeah. That's the amplitude decrease, the rate of amplitude, time derivative amplitude over amplitude. Yeah, it's the gamma. This term, if you write out the second order ordinary differential equation to describe damping, this is the damping ratio. Yeah, the gamma is the damping ratio. All right. So if this gamma is constant, then phi equal to one exact 1/2. Yeah. Then you can compute this damping characteristic by computing A over A. Yeah. Over here, for damping, they have their work is put the damping square as a damping characteristic. Now this has a critical shortcoming, is that if you put the A dot over A and square it, then A dot can be either positive or negative. Yeah, in structure, you seldom encounter A dot to be negative. In other words, the A dot is always always negative. That means the amplitude will always decrease. However, for other kind of vibration, you may have the amplitude increasing. Like imagine, what is the saturation amplitude increasing? That means as you oscillate, the amplitude getting bigger and bigger, and that means instability. Okay. In civil engineering structure, seldomly you have unstable saturation. So all the civil engineering use square as the indicator. Later I will show you that this may not be true. All right. So if we have that, then we can compute this x as gamma t, which is the amplitude decrease as an oscillation. Then you can get this. You can get gamma. And here is some of the calibrations she made. For a given frequency and for a given damping, then you can calculate, these are all given. So then you can calculate the Hilbert spectrum and compute the Hilbert spectrum amplitude. You find that the Hilbert spectrum amplitude is exactly what you're looking for. So for simple oscillation, the calibration is fine. Then she did the frequency change. Even with frequency change, she can again determine the damping as a function of frequency. So then finally, she did one more thing. That is assuming a random summation, a random damping. Then for a given damping characteristic, gamma, then she can again getting the damping characteristic. All of these are numerical computation. Then she went on and carried out a test. A test is that you have a theoretical curve of damping, and you have the data. Then you use Hilbert transformation, and immediately you plot the damping as function of frequency, just one shot. Yeah, and that make her very happy. So she actually start to do this particular frame. This is a experiment frame, and this frame is interesting. Actually, this frame is a simulation of submarine stiffener. A submarine is a tube. Inside the submarine, you have a structure stiffened to keep the keep the submarine hull from collapsing. And all this in the submarine, you want the body to be light so that you can put payload. So all these members are actually hollow. It's not solid, it's hollow. And to make the submarine damping characteristic good, so you can damp very fast, they try all kinds of way to make the damping stop on damping characteristic high. And what they did was they find that if you put plastic beads, you use very lightweight plastic, and put the plastic beads in the hollow section of the frame, that caused the damping to stop, vibration to stop right away. Yeah, and the weight is minimum, and the effective is very strong. So they are trying to study the structure for two reasons. One is to what kind of beads and what kind of density of beads and how many beads that you put in can increase your damping. Another one is that when you put a frame in here, what kind of bracing that you have in there to make the structure stronger. So these are the two things that they want to find out. In the past, they use modal analysis. So modal analysis means mode because it's a linear assumption. So what they did is to try to vibrate this structure with one frequency, one single frequency. You vibrate with one single frequency, you measure the response. And then you move to another frequency, you shake it, you get another damping. So then finally you get a whole curve. And to do that, each vibration, it will take hours to make a preparation. And so after you find that the whole structure and the whole cover the whole range of frequency, it usually takes a week or so to finish one configuration. And then you have to change the bracing from this to this to this and to nothing, and change the different fitting. Each frame will take months to finish. What they did with HHT is very simple. What they did, this is the different kind of loading, and they decide to use actually the impact load. In the past, as I say, they use periodical oscillation because it's mode. But the periodic oscillation has another shortcoming, is that your loading, when you go into the real operation, the structure is not subject to oscillatory load. Nobody will give you a force like a sine wave. The force they receive usually for submarine is received from a depth charge. The depth charge is the one that the submarine feared the most. Threw in a bomb, the bomb will explode underwater. The shock wave is so strong will actually shatter the submarine. Yeah. So the depth charge is actually impact load. So they made a certain experiment. See, in this particular configuration, they put the impact load, horizontal impact, and they measure the oscillation. Look at these two curves. It's really interesting. The empty structure oscillate, raining all the time throughout this time, which is 0.4 second, and the amplitude almost never decrease. But if you fill the structure with the plastic beads, after one impact, by this time it's already gone. So the impact, the damping characteristic is so good with the filled beads. Yeah. And this is one test, and here are different kind of bracing. the baseline bracing, the corner bracing, and the eccentric bracing. So you see the the corner bracing. Which one is corner bracing? Let's see the corner bracing. Eccentric bracing. This is the corner bracing. Yeah. So this bracing obviously is the most effective. If you use this bracing, it damp away immediately. But if you do not do any bracing, then the structure is much weaker. It will oscillate for a long time. So after this test, then you can plot up the Hilbert spectrum, and you can see the frequency, the energy as function of time. Yeah. This is baseline. This is baseline with some bracing, and you can do all kinds of this Hilbert spectrum for different kind of structure configuration, corner to corner, and eccentric bracing. These are function of time. This is frequency. Yeah. Then you summarize this. Summarize the the previous Hilbert spectrum is just energy, but we're not looking for energy. We're looking for amplitude dot A dot over A. If you plot A dot over A, what you find is this. If you spend weeks to make individual measurements, you get these dots. This is from modal analysis. You oscillate at one frequency, you get the damping at that frequency. Oscillate another frequency, oscillate another frequency. One by one frequency. You try that. This frequency is just with one bang. You take the structure, you just bang once. Bang once is oscillating. It's oscillating because its impact load impacts delta function. Delta function consists of all frequencies, almost all frequencies. And using Hilbert transformation, you immediately get this damping characteristic. This is the damping characteristic with field, that you fill this beam with plastic beam. Similarly, if you take an empty structure and you do this each individual modal analysis versus you bang it once, you see this analysis, this is just one bang. Yeah, if you bang it twice, you get another one. You can average. You bang a couple of times, a lot of this fluctuation may eventually quiet down, and you get a average. But that's just one bang. And this, you have to oscillate at a particular frequency and got the response. So you can see two things. One is that this continuous curve you obtain agree very well with the modal analysis. Yeah. And whether the modal analysis is better than this or not, heaven knows. Nobody knows. Okay. But based on theory, this should be the same if the structure is linear. And the second thing is that the field one is actually much better. The damping characteristics, damping coefficient is much stronger than the empty frame. Yeah, that was confirmed. So this make Navy so happy. They actually got a patent on this test. So in the future, they will test this, just get the structure to bend once, they get this curve, and bend another time, get another curve, and eventually they got the whole answer, instead of spend days on this each individual oscillations. And with different bracing, this is the Hilbert analysis. These are the individual. You can compare. This is eccentric diagonal. This is corner bracing. The individual crosses really agree very well with the Hilbert analysis. Yeah. So Hilbert analysis so much saves so much time and so much analysis time, so much testing time. Yeah, and again here, they are so agree so well. I have not seen this published in any literature, but I was told this is not classified, so I talk about it. Yeah, but this is a real case that the Navy feels so happy and using this so effectively. The engineer, because of this, get a lot of extra research money to do her work. Yeah. So the comparison is modal analysis versus HHT. Using Fourier modal analysis using Fourier combination of sine and cosine waves to represent a complicated waveform. So the oscillation is a waveform. So using sine and cosine, you have to use many terms. Damping assesses specific frequencies depends on the geometry of test specimen. Different structure has a different resonance mode and all that. So it's very, if you want to find out which mode that you should avoid, you have to test many times, and you're lucky if you hit on the particular frequency. The most critical thing is this work well only for linear simple system. But for Hilbert, we use a simple empirical mode function, which is AM and FM, and each correspond to different carrier frequency, and the AM immediately give you the amplitude. Yeah, so you got this. This is designed almost perfectly for damping. And the damping assessment over a continuous range of frequencies. You bend once, you get all the frequency that you need. Yeah. This is especially important if the damping varies with different frequency. For example, resonance. Yeah. The linearity condition is not imposed. They can be used to measure shock wave, especially when damping is dependent on both time and frequency. Shock is what they really want. Yeah. And for them, the shock is very difficult because you push it once, you don't know which frequency you actually got. Yeah. In here, we actually use the shock. The shock is there actually the working load. Yeah. In the submarine operation, the shock comes from attack of a depth charge. 深水炸弹 depth charge. Yeah. Okay. So the summary is that this HHT method gives a detailed local structure response behavior, and it's unique, valid, and important approach to shock data analysis. This is all her summary. Advantage of this method is effective use of full complicated data in combination of time frequency combination. And the method also fully explore of the physical significance of the IMF component, may offer new physical insight. Yeah. And this is especially for the shock impact and for identifying important structural failure mechanism of large and complicated structure. Yeah. Our work of time frequency dependent damping is the only method that's able to extract damping value from experimental study of complex systems such as underwater shock testing time series, and express damping ratio as a function of both frequency and time. And this actually solves a pretty big problem for the Navy. The Naval Surface Warfare Center means they're interested in warfare. Yeah. This is also true not only for submarine but also true for the surface vessel. If surface vessel get hit by a bomb or by a gun, the ship oscillate, vibrate too, and they want the vibration to be as minimum as possible. Yeah. So all kinds of naval vessels are subject to these tests, and this now may becomes their standard tests that the Navy use. Okay, so The damping spectrum analysis is important for non-destructive examination experiment. Damping only limited to stable structure vibration. When you talk about damping, especially the formula that you saw, that the damping A dot over A, that means amplitude change is squared. That means if the value is positive or negative, doesn't matter, it's squared, all becomes positive number. Now when the structure is unstable, that there might be negative damping. If the oscillation actually pick up and oscillation get bigger and bigger, this does not work. So the damping spectral analysis eventually lead to stability spectral analysis. Yeah, the stability is very different from simply damping. Now next, I'm going to talk about stability. Yeah. Application. Stability. Yeah. Okay. After the Navy people did the analysis for the submarine and the surface vessel, I was asked by NASA to visit the NASA center at the in the Mojave Desert, yeah, Dryden Flight Center. This place is actually the place that most of people seen this place as a test place for new cars. So this whole area is a desert. It's a lake bed. In the raining season, the lake you cannot see the end, but you can walk it all the way across because the deepest the water is about 2 feet. Yeah, it's so flat that the water just fills the whole place, miles in the end. But when it's dry, the lake bed is so flat that you can drive anywhere without any problem. So most of the airplane tests and vehicle tests are actually conducted here because there's no obstruction. You can keep driving, and lake bed is so hard. Yeah, so it's a perfect place for that. So Air Force built a big air base over there called Edward Air Force Base. If you see the shuttle, when the shuttle comes back, sometimes the shuttle comes back to Edwards when the weather is not perfect in Florida. So NASA carved out a small space out of the corner of the Edward Air Base to conduct the NASA flight test. The whole shuttle, the NASA shuttle program, is actually developed here, and it was booming when they built the shuttle. And after the shuttle was built, everybody moved away. You have a last very fancy ghost town over there. Nobody lives there anymore. What the NASA is testing, the test specimen is over here. NASA has several centers that study aerodynamics. Langley Center is the first one. They have a huge wind tunnel. But the wind tunnel, you can push the wind tunnel to a certain limit, especially if you want the test to go all the way, to go to the limit. The wind tunnel is not the place to do it because the test spacement may be shuttered. And the shutter spacement, the debris can damage the wind tunnel. So for this particular test, they actually go to Dryden, because Dryden don't have any wind tunnel, but Dryden has a fleet of airplanes. Whatever we want to test, we just hook on the airplane, let the airplane fly, and test under the flying condition. What is the spacement here? This is the fuselage of spacecraft. This black box contains all the equipment, instruments. Yeah. And the test spaceman is here. It's this little thing. This little thing is about 3 feet wide. Yeah. It's an airplane wing. This is an airplane wing. Yeah. Why do you want to test this airplane wing? This airplane wing is supposedly they're trying to do the next generation of aircraft. The next generation of aircraft has a special requirement, a special concept. That is, our present aircraft, the wings are designed to be rigid. So the airplane, after takeoff, the wing does not deform. Of course, it flutters, but it will not deform. This wing is designed so soft, so flexible. When the aircraft fly at the top speed, the wing actually deform, swing back. Yeah. And by swing back, it actually improves the performance of the wing. And also, by design, the wing so flexible, so it's lighter, so the total weight of the aircraft is less. So by having less weight and a better performance, they thought that would be a perfect solution to design the next generation of high-performance aircraft. But the problem is that if I design the wing so flexible, will the wing actually be shattered when you fly? So they want to test that. And this experiment was going on for 5 years when I first get there. The first flight is at different speed, and the final experiment was to test the safety envelope of this. They will fly until it shatters. Okay. Let me see whether the video doesn't work. Let me see if it's because of you don't have the video. Huh? Do you have the video?
Yes, next time you repeat this.
Okay. The video is nice to watch. So I want to. You sure you have the video? I forgot.幸亏带了你，要不然我这个。Okay. Okay. So what you will see is actually the video that is taken from the fuselage of the camera looking down at the wing. And as the aircraft accelerate, you'll see the wing vibrate and eventually shatter. Yeah. And the data that the data they give me. Oh yeah, that's it. 你就可以开这一个就行了。Okay. Okay, this is the wing, this is the Mach number, this is the altitude, and this is actually the it says you are clear to accelerate. Accelerate to 85 means the Mach number to 0.85. This is the oscillation, and here the sensor is put in here. See the oscillation? Yeah, the oscillation getting bigger and bigger like that. Yeah. Okay, all right, once more. this is the vibration signal. Okay. When they say terminate, it means they want to stop, but you cannot stop the airplane. So the plane, the wing was shattered. Oh, thank you. The data you got looks like this. After this point, this data are useless because the wind and the sensors are already gone. Okay, so whatever you collect here, it's totally useless. And actually, this data remind me of the data I saw in the Challenger after it exploded, and they actually recover some black box and give me data. It looks exactly like this. Means it's already disintegrated and the sensor somehow still taking data. The useful data are here. Okay, so this is the kind of data they collect, and obviously this is non-stationary. Okay, and but at that time they don't have any other way, so they use wavelet, they use Fourier, and they analyzed this data and didn't get anything. And finally, I showed them the Hilbert spectrum, and we wrote a paper which appears in AIAA journal. Anyway, so this is the data, and this data, when you decompose, you find that this data is so good. This component is 0 to 500. This component is 0 to 0.4. Okay, this is the main information. All the others, the 25 compared to 500, it's nothing. It's just a few. It's really most of this are more like noise. And after this 0 to 500, this is from 0 to 10, and all the other are so small. So even you look at this value are 0.5, 0.4. None of that is any important consequences. If we use summation of 1 to 7, summation 1 to 7, it's from here to here. If we sum up that, you look at the spectrum is perfect flat. And perfect flat means it's white noise. It's not going to be informative. And if you take the component number 8 along, you get this red spectrum. This is a Fourier spectrum. I just want to show what kind of information. This is the Fourier spectrum. If you sum from 8 to 19, consider 8 and all the rest, and you get this green. So you get a little bit extra lower frequency component, but you don't get anything more other than this lower frequency. But if you say, all right, if I take component 9 and the 19, forget about the 8, consider all the rest, and you actually get this spectrum. So the real energy is actually component number 8. Yeah, but single component, of course, is not enough. So I decide that in order to analyze this data, we should first get rid of the noise. Okay, so I get out to this. This is noise because it's a white spectrum. White spectrum has no information, and whether included or not included doesn't matter. So I decide to throw this away, and I think it's justified. And if you plot it up, this is the original data from beginning to end. Okay, and if you take away the noise is this. This is the noise. I'm sorry. This is the noise. The noise is getting bigger and bigger. Noise can come from all kinds of sources. The vibration of the aircraft, the turbulence of the air and all that. But nevertheless, all of this end up to a flat spectrum. So it is no information. If I take this away from that, I get this. This is the kind of data, Hilbert filtered data. This is the data that I want to look at. So first, I clean up the data by throw away the useless information. Once I get this, then I ask myself, what is the sampling frequency? They really want to sample this carefully. They sample the vibration at 800 hertz. So each second they take 800 data. Now let's look at something interesting. That is, if I plot a Hilbert spectrum, I immediately see that I have a lot of almost white space, but I have a very narrow energy concentration over here. The energy concentration is around, this is 0, this is 50, around 20 hertz. So I do see energy over there at 20 hertz. It's very, very important. And if I zoom in to look at the 20 hertz, zoom in instead of look at from a very large range, I zoomed in. What I see is the frequencies oscillate all over the place. I cannot see anything useful. I cannot see any concentration of energy here. And by comparison, if I use Fourier, I see a very nice concentration of energy. It's much better than Hilbert spectrum, in fact. Not only that, Fourier also show frequency, harmonics. Yeah, this is a spectrogram, by the way, spectrogram from 512 data points. Yeah, less than 1 second. So from Fourier, I know toward the end, the behavior is highly nonlinear. And the frequency is right over here, the energy concentration is here, and this energy concentration is much better than Hilbert. And if you look at the zoom in, you find that the energy concentration is much more clear than Hilbert. Then why should I use Hilbert? The Hilbert is useless. Yeah, this happened many times. The reason that I say it happened many times is that I told people that if you use Hilbert transformation, you should take a higher data rate. You take more data. But if you use every point of the data, you end up the frequency. The frequency is so diffused. So people come back and ask me, say, I follow your advice to take lots of data. Look at what I got. Nothing. No information. Okay. So what one should do? This is to filter the data. It's even better after I throw away the noise. This is very, very clear Fourier analysis. So after that, I decide to downsample. Downsample means that I take the data, I do not use every point. I take 1 point, I skip over here. I skip 8 points. So I reduce my sample to 100 hertz. Yeah. So if I reduce my sample to 100 hertz, I will get 8 sets of data. Each set looks like this. So if I plot the 8 sets, it still shows the oscillation okay. It may have a little bit of detailed difference, this wave versus that wave. Yeah. But nevertheless, the basic frequency is still there. The basic frequency is what I want, right? Therefore, this downsample is useful to me. Then a very critical point here is that should I downsample once I collect the data right away? The answer is no. If you downsample with your raw data, what happens is that the white noise will come in. You will never get a very clean data. So you first throw away the noise and then downsample. So the noise only gives you perturbation in here. It will not give you any information. So you first filter it, throw away the high frequency, and collect the clean data. Once you collect the clean data, then you can then you downsample. Once you downsample, then instead of one set of data, you actually get 8 different spectrums. And this 8 spectrum you average, you will get a much better reading. This is the downsampled 8 averaged Hilbert spectrum. Yeah. Now you see that the energy get bigger and smaller, larger and smaller, eventually get very, very large, and then the frequency decreases. Yeah. This is what you really want. And also, there are low frequency energy that actually creep up and becomes very high. And compare this with that, you will see the difference is so big. Yeah, this you cannot see anything. Why you cannot see anything? Because you take a derivative of the frequency. And any small change will give you a large frequency deviation. The answer will never actually concentrate in the range that you would want. Yeah. So this downsampled data is really useful. This is filtered, downsampled mean spectrum, Hilbert spectrum. And this Hilbert spectrum, when you compare the the marginal spectrum, this is a Fourier spectrum of the data, cleaned, filtered. This is the Hilbert spectrum that you got. What do you gain? You gain the bottom of the spectrum is over here, the top of the spectrum is over here, versus the Fourier, bottom is over here, top is over here. You gain more than 1 decade of resolution. So the resolution is much better in the Hilbert spectrum analysis than Fourier analysis now. So the peak is much clearer. And you can plot this spectrum up. You see that this is where the highest energy, this is function of time. This is the energy actually move from here over eventually to this. And this energy, original here and eventually come up to here, is what they call the stress stiffening. So something which you apply a little bit stress, actually the material becomes stiffer. And as the material becomes stiffer, the frequency actually jump up. This is the first reaction of the material. Once you apply load, the structure becomes stiffer. And when you apply load, by the time it yields, the frequency actually decreases. That's just before the collapse or the shattering. So you can see a different view of this is the spectrogram. The spectrogram, and if you look at this and compare this to spectrogram, they look about the same. Okay? But the important difference is that if you plot the instantaneous frequency of the 8 different spectrum, you get this figure, and finally you see a instantaneous frequency decrease. And you can expand it out to see this 8 different instantaneous frequency value, and here is your mean of the 8. The mean of the 8 actually shows a drastic decreasing at the last moment. How long the last moment lasts? Lasts less than a second. And that's why the pilot says, stop, or knock it off. It's too late. Because in 1 second you cannot respond. This is 116.5, 117.5. This in between here and here is just 1 second. Yeah. And and you can look at the standard deviation. The standard deviation is here. Yeah. The reason that I can get the standard deviation here is that I used the zero crossing rather than Hilbert transform. The zero crossing, I have you can see the steps, and this is very clear that you get 8 different cases. In the average of 8 cases, you get the upper and lower standard deviation. And if you look at the different sections, the standard deviation is almost within the data width. So it's very clear. Now you compare. I show you that the spectrogram and the Hilbert looks almost the same. Now why should we use Hilbert? The key difference is here. Using spectrogram, you will never get the bitter end because you have a block average. Finally you lost 1 block. Yeah. But that's one last block is precisely where everything interesting is happening. Yeah. And the happening blow up is that the frequency almost constant, and by this time it suddenly decreased. Yeah. And Fourier never actually captured this part. Yeah. The whole thing they want to study, they did all this study, is they try to capture how it fell. Yeah. And when you plot the data and plot the filtered data, you see the difference. The blue is the original data. This red is the filtered data. After I throw away the noise, so after you throw away the noise, the dynamics is much more clear than the previous one that the data plus the white noise. And if you look at the last second, what happened is this. See, this is the instantaneous frequency. Instantaneous frequency fluctuates, and by this point it starts to decrease. And the point in which it starts to decrease coincides with the amplitude. This is the envelope of the amplitude. The amplitude increase to this point and level off. And here are 2 lines, the data and the filtered data. So I have already thrown away some filtered data. So you compare these two, you find that as the amplitude level off, the frequency starts to decrease. What does that mean? That means the amplitude of the wind originally start to flutter, and the flutter amplitude keep increasing. By this time, it yields. It yields means that just like you bend the metal, before it breaks, the strength give away. And when the strength give away, when you bend, it has offer no resistance. As it offers no resistance, the frequency decreases. Yeah. So as the wind lost resistance, the frequency starts to decrease. It's the total yield of this. And as it yields, it's totally different characteristic. So the nonlinear effect should be most visible over this range when it's still resisting, but resisting differently. So from that, we decided we to look at the stability spectrum. The problem of the previous approach is the Hilbert envelope contains modulation amplitude, define both positive and negative damping. Yeah. Then they define instantaneous frequency. This is the same as previously A dot over A. Yeah. But instead of this square, we don't use the square anymore. Okay, so the difference, we don't use square, then we have positive and negative. Now here, a very critical point is that what kind of amplitude should you use? The amplitude, look at the amplitude. If you use, this is the data, clean the data. If you use Hilbert transformation, this is the amplitude you get. And if you use the spline, this is the amplitude you get, smooth amplitude. There are two sets of amplitude. In the previous study, the study by the Navy, they actually use Hilbert amplitude. And I told them the Hilbert amplitude is not very good and almost useless in study damping and stability. The reason is that the Hilbert amplitude has its own fluctuation. This own fluctuation is caused by some of the nonlinear property of the data, mostly nonlinear property of the data. So you see this, if you take the derivative of the Hilbert amplitude, the derivative looks like this. That's the derivative. But the Navy people say, okay, it has negative and positive, I only take absolute value, so they don't care. But I do. If you use the slope to take the smooth, the derivative looks like that. Now this actually is the average of that value. Large positive and large negative value derivative average doesn't make sense. So you have to really get in the mean before you take a derivative. So this is the spline envelope. And for different, even if you start to average like a 5-point successive average, the Hilbert envelope still doesn't work. And this is much better. Yeah. And 21 point smooth. Even after 21 point smooth, you have to notice the sign. Here is 60, here is 15, here is 4. So if you, after you use 21 point average, the Hilbert amplitude still fluctuates quite a bit. Yeah, but the smooth derivative is already very well behaved. And this is another thing that we find. The smooth amplitude is important. The smooth amplitude is not only important here, but it's also important in normalizing the signal when we compute instantaneous frequency. In other words, you have a frequency, the frequency is, say, IMF. You still cannot immediately compute the instantaneous frequency. You have to smooth it. You have to separate the signal into AM and FM. And you can only compute the instantaneous frequency on the FM part. You should separate it from the AM part. Yeah, and this is the AM part. And that is critical in applied Hilbert transform. I have encountered many questions people ask me, so it doesn't work because they did not separate AM FM correctly. Yeah, the AM and FM part, unfortunately, you cannot use the nice Fourier-based Hilbert transformation. You have to use the separation, the smooth separation that I propose. All of this, next time I will give you a summary. All of this indicate that this whole method that I'm using, that I'm trying to advocating, I'm trying to give you, actually works. But that defies mathematicians' rigorous definition. This is one of the reasons. If you try to define amplitude by Hilbert, you'll get this kind of answer. If you define amplitude by this answer, it's much more reasonable. So once you do that, then you will get, once you use this, use this definition, you'll get a more reasonable thing. Then we define stability spectrum as as A dot over A with the sign intact. But then there are other problems. A dot over A is very sensitive to A. It's A dot fluctuation over the amplitude. When the amplitude is small, then A dot over A can be very big. That A dot means slope, but it depends critically on A. Therefore, there has to be an amplitude cutoff. Yeah. So the stability spectrum has to have a percentage cutoff. Let me just show you the percentage cutoff. This is a percentage cutoff 0.001. So that means I take any amplitude, yeah, including the 1,000th of the largest amplitude. This is normalized. So 1,000th of large amplitude. Then you see that the contribution actually come from everywhere. Many of these places are coming not because the stability parameters is big. The large stability parameter all come from very small amplitude. Okay, so this is 1,000th, and this is 10 time step average. And if I use 5 parts per thousand, look how clean it becomes. And if I use 1 part per thousand, look at it even cleaner. And this is 1%. 1%, that means I cut off anything less than 1% of the amplitude. Yeah. And I can cut off even more, 10%. Then all I have is this. That means the instability only occurs at the last minute. And this is very reasonable. This is very reasonable answer. Yeah. So if you want to study a problem, then what that means is that you have to go through a number of the steps. That each step you see the physics, you see the value, and what it costs the effort to fill. It is actually happen all at the last moment. Previously, the flutter may go bigger and small, but that does not imply unstable. The real instability is right at the bitter end. Yeah. So this percentage is important. Here we hold the time step average constant, and if you use percentage of 0.1, 0.01, 0.51, you see the amplitude contribution as a function of frequency. You see this is 0.1 is here, and 0.001 is here. So if you take too small a amplitude, what you will experience is a lot of this frequency all comes in because of the small amplitude. And if you plot this as a time, the business end is over here. This is plotted as a frequency. The frequency is very, very low frequency is the important one, and this is plotted as time. The very critical period is the last seconds. Yeah. So in this way, you look at a different frequency, you look at a different time, you identify your problem. Yeah. The problem all happen over here. Then the effect of smooth. If you vary the time average, so this is with 3 time steps. You have a lot of specular return signal, and 5 time step, and 10 time step, and 15 time step, and even 20 time step. As you move your time step average with a fixed percentage, then you will see that the average energy comes from, you can see the energy come from a more smooth, averaged area. So whether these actually are positive, these are negative. That means this area in general, other than these few spots, this area in general are stable. Yeah. And when you come to here, it becomes unstable. And mostly unstable. And with even longer, then you see the time average spread out. This is plotted as a time average. You see the more you average, the smoother, of course, the answer will be. Yeah. And as function of time, again, the important phenomenon is toward the end. All over here, nothing much happened. Yeah. So nonlinearity. I have talked about Tigger's energy operator. Now, if we use Tigger's energy operator, we'll see that Tigger's energy operator, this whole wind oscillate, becomes nonlinear almost everywhere. Yeah, this such flimsy, such flexible wind, the deformation is always over the elastic limit. And if you look at it toward the end, so just before it starts to break off, this is starting the break off. Here, it becomes highly nonlinear, and then it starts to yield. And once it starts to yield, the linearity is not an issue anymore. Yeah. So this is the big critical point. And if we, at this point that we stop, then we can save the amplitude from decreasing. So here's our conclusion. The conclusion is that the flutter is quite nonlinear. It's nonlinear from beginning to end. It's not just any particular instance. And the flutter frequency increase with increasing Mach number. That means as our airplane speed increase, as you see, the load is increasing. As the load increasing, the structure has a stress stiffening. Even Fourier point of view, there's a faint subharmonics vibration, which suggests nonlinearity. When you look at the Fourier spectrum, you see a lot of harmonics. That harmonics indicated that the waveform is already distorted. And distortion of the waveform suggests nonlinear. So we know that they are nonlinear. Nonlinear becomes obvious toward the end of the test, and especially after the flutter starts increasing. Yeah. The nonlinear vibration is confirmed by Fourier-based spectrum, which show second harmonics, and just before shatter of the wind, the flutter frequency starts to decrease. Yeah, decrease means the wind actually starts to yield. The frequency change at the end cannot be detected quantitatively by any other method other than Hilbert transform. Yeah, the stability spectrum with different magnitude, the cutoff, smoothing, and all. For tentative guide for this particular thing, we suggest the percentage larger than 1% and time step smooth less than 20. I do not have a definitive recommendation here. I only suggest that less than 1%, it shouldn't count, because the small amplitude give you sometimes spurious high reading in the stability index. The reason is that we are looking for A dot over A. Small a contribute as much as large A dot. Okay. the last one is that over most range, the wind actually is unstable with negative stability index. Yeah, that means negative damping. So this is important. In the past, most civil engineers use damping as a characteristic to characterize the building or structure. They only worry about the positive damping. The reason they get positive damping, however, is that if you look at their derivation, even negative is counted as positive because they get a square. If A dot over A is negative, they square it, it becomes positive. So in their calculation, there are lots of instability actually is counted as a stability, as damping. So you have to be very, very careful. And because of this study, we not only publish a paper, we also have a patent on this, stability spectrum analysis. Yeah, means the stability spectrum analysis. It's not a right now. It's not a standard tool. So what I did with the data is that I looked the data with various parameters. I explore the parameters. I explore the cutoff frequency. I explore the averaging in time. So eventually, I get a very clear sense of what's going on, and I finally identify the instability actually occurred toward the end. That's I give them the quantitative answer. So Dryden was very happy for this analysis. Yeah, and after that, they asked me to go over there to give them a short course on this. I don't know whether they are still using it or not, but I think if they are going to analyzing future experiment, this tool is probably going to be very helpful to them. Yeah. Okay. I think this is the end of the stability. Yeah, that's the end of this. So we only have one more lecture to go. So next time we'll meet, I will give you a wrap up of all we discussed, summarize the effort of the whole semester, and maybe becomes a little bit philosophic about the methodology. Okay. All right. Thank you very much. Any questions? No? Yeah.
I want to go back to.
Okay. Mm-hmm.
There should be two status. One is force vibration by the truck, and another is free vibration due to the initial displacement. And how can we figure these two status from this figure?
No, I cannot. But most of the vibration, however, are actually free vibration. The forcing, see, you put the sensor right on top of the pile, right over here, okay? So the truck was passing by the direct load in, I don't know, very short period. It's probably just that little period. Yeah. Now, whether however, even before the truck even get on this, it starts to vibrate already, okay? So the vibration, this frequency, most likely is this frequency is the proper frequency of the pier, and they made some preliminary estimate of the proper frequency. It's around this value, 1 point something. I forgot exact. Yeah, it is hard to separate the truck vibration. Usually the truck vibration are low. The truck is mostly mechanical vibration. It seldom vibrates at 1 hertz or 2 hertz. Yeah.
But if you have a lot of trucks come and you don't
know which one.
Yeah.
Well, fortunately, in here, as in the span in the deck, we never stop any traffic. We just let them go. Okay. The big truck, compared with the small car, actually the big truck the signal is much stronger. Even the noise level can overwhelm the small car. But if we have a strand of like a train of truck, 20 in a row, I don't know what will happen in that case, but I still think this frequency will probably show up. Will probably show up in even under that condition, because the truck, whether this is truck or not, I don't know. Yeah, but I tend to believe this is the truck. A truck. This actually happens when I average over different cars, small car, big cars. These two frequencies all appears. Now you would think that for a small car, like a small automobile, its frequency will be very different from the truck. But these two frequencies doesn't change. And using those two conditions, I believe these are the structure vibration, not from the truck. Yeah. If you are interested in that problem, I suggest a book you may want to read. Professor Yang has a book called Truck and Bridge Interaction, or Truck Rail Interaction. It's available.
Another question.
Sure.
Because you say that the two frequency is from pile, and if we take these two IMF out, can we identify the crack of the pile from the modulation of amplitude or the frequency?
If we take this particular frequency component out, you'll find that this pile oscillate at say like 16 hertz, 1.6 hertz. The other pile oscillate at 1.2 hertz. The difference is the other pile has already exposed. So it's not the crack, it's the foundation that's exposed. Remember at the beginning of the class, this is the pile we'll talk about. This is pile number 2. Yeah, this is the pile number 1. See, this pile, we put the sensor here. This pile all exposed, and because it's exposed, it's so wobbly. And we compare this pile with all the other piles. Their frequency are the same. And not only the frequency are the same, the two peaks are all the same. Remember, we plot the particular frequency. No matter what kind of car pass by, the frequency doesn't change, except this one. Now, this is pile number 2. Yeah. We actually, we even tried to put a sensor on here. We didn't get anything meaningful. So actually the data we got is from here, outside the rail, but on top of the pile. Yeah. Okay. Yeah. Sure. Yeah. No. No. You downsample the clean up data. The reason that you don't want to downsample the raw data is the raw data has high frequency noise, right? So when the high frequency noise is, the amplitude is not small. Okay. This is raw data. This is the cleaned data. So if you do not clean first and you start to downsample, one point may be here. The other point may be here. Yeah. So as a result, because of the noise, it's so big, and noise frequency is so high, you'll never be sure that where you got your point. You may get one point hit the peak, the other one hit the trough, and as a result, your data will be scattered all over the place. The downsample, the critical part of the downsample is that you want to get some signal which is not really totally random. Okay, you want each data to be representative of the phenomenon. So you want to get rid of all the noise before you do the downsampling. Yeah, the filtering that I suggest is use Hilbert, and many people do it against my suggestion. They use Fourier to filter the data. Using Fourier to filter data, you can still get rid of most of the data, but you also get rid of the harmonics of the basic oscillation. So then the waveform you got will be more linear than Hilbert filtered the data. Okay, so the downsample should definitely be done on this red data rather than the blue data. Yeah, the blue data, you can see how large the difference. In fact, your data is only that much. This difference is already a significant part of your data. Yeah. So downsample should be done on the clean up, especially here. Look at this. This is your clear signal. Look at how large the fluctuation that you could get. And the noise, as we demonstrate, is white. So it does not give you any more information, even if you include it. Okay? All right. Any more questions? No? All right. We'll stop here. The class is dismissed. Next time will be our last class. I will be just maybe talk about something in general. For you people come from Taichung, I think you may want to save the trouble. Okay. All right. Thank you very much.